Hello, in this lesson we're going to focus on how to calculate the volume of a solid of revolution using definite integrals. And the method that we're going to be looking at today is called the disk method and then the washer method. And we're going to start by developing a formula for the disk method. Suppose we want to find the volume of a solid that's obtained by rotating a certain region around the x-axis. And the region that we're rotating is the region formed by y equals f of x, y equals 0, x equals a, and x equals b. So if you can imagine taking this region right here and then rotating it around the x-axis, we're going to get a solid figure. And we're trying to find the volume of that figure. But first, let's just figure out how we might calculate the volume of one disk. And what do I mean by one disk? Well, if we just focus on one of these rectangles, not all of them, but just one of them, if we take one rectangle and rotate it around the x-axis, what is that going to look like? So we're going to take just one arbitrary rectangle and rotate that around the x-axis. So when we rotate that around the x-axis, it's going to create a shape that just kind of looks like a longer rectangle when we look at it from this orientation. But if we were able to look at it from the side, a side view of this, imagine what shape that's going to make. It's going to look like a circle when we look at it from the side. So what we're actually creating here is a circular disc, and I'll try and draw it a little more three-dimensional. We can see our disk here. We want to figure out what is the volume of this one disk. Well, this is a cylinder, and we know that we can find the volume of a cylinder using just the area of the face. So the area of the face of the cylinder, and again, we have to imagine that we're viewing it from the side. So this is a circle right here. The face is in the shape of a circle. We want to multiply the area of that circular face by the height of the cylinder. And this is the height of the cylinder right here. So let's go back to our graph and just label one of these rectangles as our arbitrary rectangle that we've chosen. So it has some x value down here. And if we think of the very first rectangle as having an x value of x sub 1 on the right end of that subinterval, and then the next one x sub 2, and so on, then when we just get to an arbitrary rectangle, I'm going to call that right end point of that subinterval x sub k. And if this is x sub k, this input value here is x sub k, and I follow that up here, this is f of x sub k, because this point is on the function f of x, where the input is x sub k and the output is f of x sub k. So going back to finding the volume of our disk, we know that the volume of a cylinder is just going to be pi radius squared times height. And in our case, the radius of this disk is this vertical distance right here. Or going back to my graph over here, it's this vertical distance. That's the radius of my disk. And what is that vertical distance? Well, it's the top y value minus the bottom y value. The top y value is f of x sub k. The bottom y value is just y equals 0. And the height of this cylinder, where it's oriented sideways, but the height of the cylinder is just delta x. The width of each one of these subintervals on my graph here is delta x. Each one has the same width. We're setting it up that way on purpose so that each rectangle has a width of delta x. So now we can rewrite our volume for our disk as pi. Radius squared becomes f of x sub k squared. And then the height is just our delta x. And And we could write delta x as dx also. We are going to jump to that eventually. So now let's think about how we would express the volume of the entire solid, not just one of these disks, but the sum of all of these disks. If we want to add up the volume of all of these disks, and we don't want a finite number of disks, we want infinitely many, so that the width of each one of these subintervals is approaching 0. Our delta x is approaching 0. We can accomplish this using an integral, and we saw this when we were working with Riemann sums, how we translate from a Riemann sum with infinitely many subintervals to integral notation. So we will be able to find the volume of the entire solid if we add up the volumes of all of these disks, infinitely many disks, on our interval. And our interval goes from a to b. So it starts at x equals a, it ends at x equals b. And then we have pi f of x sub k squared. Now I can drop the k in the subscript and just say f of x. Because when we actually compute the Riemann sum, like the summation takes care of that k. And then the delta x we're going to rewrite here as dx. So this is going to give us a way, using a definite integral, to calculate the volume of this solid of revolution. Let's look at this example. Find the volume of the solid obtained by rotating the region bounded by y equals the square root of 2x. So that's the blue curve that we're seeing here. Y equals 0, that's the x-axis, and x equals 1, that vertical red line that we're seeing there. So the region that we're looking at is this region right here. That region. We're going to rotate that region around the x-axis and find the resulting volume. Now before I do anything else, I'm going to determine the interval on which I'm working. So I can see that one end of my interval is at the origin here, 0, 0. And then I also need to figure out what are the coordinates of this point right here. This is the graph of x equals 1, so I know this point here has coordinates 1, 0. And then we may or may not need to know the coordinates of this point, but I will go ahead and find that as well. So that's the point of intersection between x equals 1 and y equals the square root of 2x. So we have y equals the square root of 2x, and we want to know what this is equal to when x is 1. So if y equals the square root of 2 times 1, then y is just the square root of 2. So the coordinates here would be 1, square root 2. Now the next thing I would typically do would be to draw my reference rectangle, but it is already drawn in the figure here for us. And this just represents one arbitrary rectangle in that Riemann sum that we're using to set up this problem. Because this is a vertical rectangle, I know that the width of the rectangle is just the change in these two consecutive x values. It's this delta x right here. But instead of writing delta x, I'm just going to write dx. So that serves as a reminder for me that I am setting up a dx problem. So my volume, I know when I set this up, it's going to have a dx at the end, not a dy. This is a dx problem. Okay, next, I know that the basic volume formula is going to be pi r squared times h, or pi radius squared times the dx, where this is the radius. Because if I were to rotate this rectangle around the x-axis, I'm creating a disk here. This is my circular disk. Okay, that drawing is a bit messy. But we've got the face of our disk here. That's the circular face. So my radius is a vertical distance here, and it's just the top y minus the bottom y. So the top edge of this rectangle is touching this function y equals the square root of 2x. And the bottom edge of that rectangle is just touching y equals 0. So that vertical distance is the square root of 2x minus 0, or just square root of 2x. Okay, so I need pi, and then my radius squared, and then times dx. So let's clean this up a little bit. The pi is a constant multiple, and we know that we can bring a constant multiple outside of the integral. So I will do that. And then this needs to be a definite integral, so we have to write down our bounds. Because this is a dx problem, I know these are x values. I'm going from x equals 0 over to x equals 1. Right? X equals 0. This is where, if I were to draw all my little rectangles in here, that's where the rectangles start. Over to x equals 1. Again, if I were drawing all my rectangles, that's where the rectangles would stop when x is equal to 1. Square root of 2x squared dx. Okay, so there is my setup. And now we just need to compute the answer. So let's evaluate this integral. So this is pi times the integral from 0 to 1. The square root of 2x squared is 2x, then dx. So pi, then I will integrate the 2x dx to get x squared from 0 to 1. And we know for that we're going to sub in the upper bound, so 1 squared, minus, and then sub in the lower bound. And my final answer is just pi. So the volume of the solid is just pi. Now we are also asked to sketch this resulting solid, so let me clean up the diagram a bit here and see what we can do. So when you are sketching, what you want to do is reflect your region across the axis of rotation. So I'm kind of just going, by symmetry here. I'm trying to go look the same distance away from the x-axis. So that's probably about right there. And I'm just going to reflect that. Okay, that's not perfect, but it's somewhat close. And then any vertical lines, in order to just kind of give them a little perspective, we're just kind of bend them a little bit. So instead of having that straight line at the edge, we're going to bend it and just make it look kind of circular. So this would be the outside of the figure here. And then this would be like the interior here. So let's review the formula for disk method. And this is the formula that you're going to use when you make a vertical slice. And by vertical slice, let's go back to our image. By vertical slice, we mean we're slicing vertically this way to get a cross section. It's another way of saying you're going to use a vertical rectangle when you're using your setting up your Riemann sum. So that's all we mean by vertical slice. This rectangle is a vertical rectangle. So let Q be the region that we're rotating. The volume formed by revolving region Q about the x-axis is given by this formula right here, and it's basically that pi r squared h, finding the volume of that cylinder. It's a dx problem, so the lower limit of integration and the upper limit of integration are both x values. Now we can also set up this disk method using horizontal cross sections, or a horizontal slice, or horizontal rectangles. Suppose we want to find the volume of the solid obtained by rotating the region bounded by x equals f of y, so that would be right here, x equals 0, that's right here along the y-axis, y equals c, and y equals d. So here's our region right here. And this time, we want to rotate that around the y-axis, not the x-axis, but we're going to rotate around the y-axis. How can we represent the volume of one disk? Well, this time, if I take a rectangle, I'm just going to pick one, this one, and rotate it around the y-axis, then my disk And again, we have to imagine now looking at it, from this direction. But this disk has a height here of dy, or delta y, instead of dx. And the radius of this cylinder is just this horizontal distance. To find horizontal distance, we take the right endpoint x value minus the left endpoint x value. So we'll just look at this rectangle here, and we'll follow this down, and we'll just say that's x sub k. Then this is y sub k. And the x value right here, I can't write f of x sub k because f of an x value gives you a y value. We're actually trying to write an expression for the x value. So it's f of y sub k, because here x is a function of y. Right here we see that x is a function of y instead of y being defined as a function of x. So our radius is f of y sub k minus 0. So going back over here, our volume pi, and then our radius squared times the height of the cylinder, which in this case is dy, or delta y. The expression for the volume of the entire solid, then, we'll use an integral from that. This is a dy problem, so we need y values for our lower and upper limits of integration. We're going from y equals c, that's the lowest y value here, all the way up to this y value up here, which is y equals d. So we're going from y equals c to y equals d. The pi is a constant multiple, so we can bring that out. F of y, the k is going to disappear as part of the summation, so I'm not showing all the details here on how we got from the expression in number 1 to the expression in number 2. But I guess in between here we have a Riemann sum, and we're using a limit. We're taking the limit of a Riemann sum. And as part of that work with the summation, the k is going to disappear. Find the volume of the solid if we rotate the region bounded by y equals x squared. So that's this graph right here. That's our y equals x squared. X equals 0. That's right here. And then y equals 4. So y equals 4 is this equation right here. We're going to rotate, so this is our region. Here, it looks better if I shade. This is our region, and we are going to rotate that now about the y-axis. Rotate around the y-axis. So I want to label my endpoint so I know what interval I'm working on. This, of course, is the origin, 0, 0. And right here, since this is the equation y equals 4, this point right here has coordinates, not 4, 0. But 0, 4. And this point, I know the y-coordinate is 4. What's the x-coordinate? Well, we can use the equation of the parabola to help us figure that out. So 4 equals x squared whenever x equals 2 or negative 2. So this one, of course, is the positive 2. We're just not seeing the left-hand side of the parabola. So next step, draw the reference rectangle. It already is drawn here for us, so I'm just going to label this now as a dy problem. Whenever my rectangle is oriented horizontally, I like to label it immediately as dy, so there's no confusion when I'm setting up my integral. I know that when I set up my volume, it's going to be a dy integral now, not a dx, and that immediately tells me that these are y values for my lower and upper limit of integration. So we're going from down here. If we were to draw all of these rectangles, right? If we were to draw, which of course we can't because there are infinitely many of them and they're very, very tiny. But we'd be going from y equals 0 all the way up to y equals 4. So we're going from y equals 0 to y equals 4. And then I know my basic setup is pi radius squared times the dy. So pi, that's my constant multiple, and then I just need the radius squared. And my radius is that distance right there. It's a horizontal distance, so I need the right x value, so right here, what does x equal, minus the left x value. What does x equal there? Well, on the left, that one's easy because it's on the y-axis, x equals 0. On the right, what does x equal? Well, we haven't been told exactly what x equals, but we do know what y equals right here. We know that y equals x squared. And so we can solve that for x, and we get x equals plus or minus the square root of y. Now, do we use plus or minus, or do we just use plus, or do we just use minus? Well, let's think about this. The equation is telling us what x is equal to, and we clearly can see that all of the x values in our region here are on the right side of the y-axis, and x values on the right side of the y-axis are positive. So we will just use the plus, not the minus. So x equals square root of y. If we had this half of the graph over here, then that would be x equals negative square root of y. But we do not. Okay, so right x minus left x. It's just square root of y minus 0 squared dy. That's our setup. That's our volume right there. And we can clean this up a little. Volume equals pi integral from 0 to 4, the square root of y squared. The square root of y squared is just y dy. And then we're ready to integrate that. The antiderivative of y is y squared over 2, and we're evaluating from 0 to 4. So we sub in our upper bound, we get 16 over 2, minus, sub in the lower bound, we just get 0, and so our final answer here is 8 pi. So let's take a look at the formula then for using disk method with a horizontal slice. Horizontal slice, and let's go back to the graph for a moment. We're saying horizontal slice because we are slicing this way to get all of our disks. We're slicing in a horizontal direction, and we can tell very easily that it's horizontal slicing because the rectangle is oriented horizontally. Okay, so the setup is very similar as it was when we used a vertical slice. It's pi as our constant multiple, radius squared times the height of that cylinder, which in this case is the dy. So all comes back down to pi r squared times the height. And since this is a dy problem, we're using y values for the lower and upper limits of integration. Okay, let's find the volume of the solid formed if we revolve the region bounded by y equals square root of x, so that's the blue function, and the line y equals 1, that's the red function, from x equals 1 to x equals 4, around the line y equals 1. So this time we're not rotating around the x-axis or the y-axis, we're rotating around the line y equals 1. So here is our region that we are rotating right there, and we are rotating around this line y equals 1. So we want to find these points of intersection. So this is 1, 1, and then we have this point here. We can see that x equals 4, and it looks like y equals 2, but we should verify that. We can verify that using this equation right here. So if we have y equal 4, no, x equals 4, then y equals the square root of 4, so y equals 2. So this is 4, 2, and then this point right here, we know this is the equation y equals 1, so this would be the point 4, 1. Next, we're going to label the width of our rectangle. So this is a dx problem because it is a vertical rectangle. If I were to draw my disk, I'm just going to reflect my rectangle across the line of rotation, and then just try and make it look three-dimensional. We've got that circular face on the side. There's my disk. So our setup now, volume equals pi, and then we're integrating. I know this is a dx problem, so these are x values here. Our interval goes from x equals 1 to x equals 4. And I need radius squared. The radius of this disk is this vertical distance right here. So let me erase some of this so we can see what we're doing. The top of this rectangle, we need the top y minus the bottom y. So the top y is just that equation, y equals square root of x, and the bottom y is coming from that red equation, y equals 1. Okay, so here top minus bottom is square root of x minus 1. That's my radius, and I need to square my radius, and then I need to multiply it by dx. So there's our setup. Now to work out this integral, I am actually going to expand the square root of x minus 1 squared. Let's FOIL that out. So we're integrating from 1 to 4. First times first. The outer product is negative root x. The inner product is also negative root x. So negative 2 root x plus 1 dx. And then we can find the antiderivatives. The antiderivative for x is x squared over 2. And then for the 2 root x, it's easiest for me if I think of that as 2x to the power 1/2, and then I'm using the power rule. So I'm going to add 1 to the exponent, and then divide by the new exponent. Dividing by 3/2 is the same as multiplying by 2/3 times the constant multiple that was already there. Now we're going to sub in our upper bound 4. So 4 squared is 16 over 2 is 8 minus 4 to the 3/2. We're going to do the half power first. 4 to the half power is 2. 2 cubed is 8. 8 times 4 over 3 is 32 over 3. Plus 4 minus, then we sub in our lower bound. So 1/2 minus 4/3 plus 1. And that all simplifies to 7 over 6 times the pi. So 7 pi over 6 is my volume. When you're using the disk method, you always want to draw your picture. You always want to label your reference rectangle. It seems like an extra step, but it's really important in helping you to set up the problem correctly. And when you're using the disk method, make sure when you do draw your rectangle that it's always perpendicular to the axis of rotation. That's the key to setting up the disk method properly. Your rectangle has to be perpendicular to the axis of rotation. At this point, I'd like you to pause the video and try some of these practice problems. The one that is indicated as a calculator problem, after you set it up, you can just use the Math 9 on your calculator to compute the value of the integral. And here are those answers if you'd like to check. Next, we're going to talk about another method for finding the volume of a solid of revolution. So it's very similar to the disk method, but there is an important difference here. Suppose we want to find the volume of the solid obtained by rotating the region bounded by f of x and g of x equals a and x equals b, about the x-axis. So I want you to try and visualize this for a moment. If we take this green rectangle that you're seeing right here and rotate it around the x-axis, what shape are we going to get? Is it going to be a disk? Now, I don't quite have enough room, but if we imagine reflecting this rectangle across the x-axis, we can see that there's this empty space here in between that doesn't get filled in. It's not solid, it's empty. So imagine spinning that rectangle around the x-axis. What is that shape going to look like? Well, let's imagine we're looking at it from a side view. not straight on like you're looking at your screen right now. But if you could somehow, turn your head and look to the side of your screen, what is that going to look like? Well, we should be seeing a circular disc, except that there's a hole in the middle of it. There's this hole there, and it's got some thickness to it, whatever the thickness of that rectangle was. Right, so we don't call this a disc, we call this a washer. It's like a disc, but it's got a hole drilled through the middle of it. This is a washer. And we want to find the volume of this. Now, if that hole weren't there, we could just use the disc method and find the volume of the solid. So the strategy we're going to use here is to find the volume of that empty space. If we can somehow, reverse this and make the hole filled in and the rest of it not filled in, what would the volume of that hole be? And then we can just subtract the volume of the solid, as if it were a disc, minus the volume of the hole, and what we have left would be the volume of the washer. So the volume of the disc would be pi, and then the integral from a to b the radius. Now we have to be careful here. Is this the radius? If we were doing the large disk, let's go back to this picture over here, the radius of the large disk would be here. So it wouldn't stop at the bottom of the rectangle. It actually goes all the way to the axis of rotation. That's what the radius is. And we're going to call this capital R, like big radius or outer radius. So big R squared dx. That would be the volume of the disk. Now, if we wanted to find the volume of the hole, the empty space, the radius would just be that distance right there, right? It's just that much right there. So we're going to call that one little r. Pi, still on the same interval, we're going from x equals a to x equals b, but now it's a little r squared dx. So the big disk minus the, and really we're using disk method for the hole to find the volume of that empty space. We're just doing a big disk method minus the little inside disk method. So we need to subtract this one. And because these two integrals are both being multiplied by pi, the same constant multiple, and they both have the same lower limit of integration and upper limit of integration, we can actually just combine these into one single integral. So instead of two separate integrals like this, we can go ahead and put them together in a single calculation, like so, going from x equals a to x equals b, big R squared minus little r squared dx. And that's going to be our basic setup for this washer method. Let's consider this problem and break it down. So first we would find the volume of this outer larger solid, the outer disks. And we've got an image on the right to show you what that would look like in 3 dimensions. We have this cone shape. And to calculate that, we would set up an integral from a to b, and it would just be this distance here, so f of x squared dx times pi. So that's not the answer we're looking for, but this is kind of our first step. This is the volume of the outer solid. Then we would want to find the volume of the inner solid, just using this little distance here as our radius. And so what we're finding there is what we would get if we just rotated this thing, this region right here. Let me shade it in. Just this region right here around the x-axis. So that one looks like a funnel. And the volume there for that inner piece is going to be the integral from a to b times pi, and then g of x squared dx. And then step 3 would be to find the difference. So take the outer solid's volume minus the inner solid's volume. And you can do this in 2 separate integrals, or as I said, we can put them together and write it as one integral. So our final answer, we're integrating from x equals a to x equals b, pi, which I can bring out or leave in, either way, times f of x squared minus g of x squared dx. And you can see in the image here how I've stacked one rectangle on top of the other. We've got the outer rectangle, this representing the, if we did a disk method for the outer function, minus, and then here's our little rectangle for the inner function, our inner disk. So you can see each rectangle can lay on top of one another like this. Now when I actually draw it, when we start a problem and I'm drawing my own rectangles, I normally don't stack them one on top of another because it makes it difficult to label things. But it is a more accurate representation if we do draw them stacked like this. Normally what I would do though is I would draw my outer rectangle and then I would just draw the inner rectangle somewhere else. But keeping in mind, so here that representation isn't completely accurate because we are really subtracting, like it should really be here. This is the inner rectangle that we would be subtracting, that piece of it right there. It just gets difficult when you draw one on top of the other and you're trying to label things in your diagram. It makes it difficult to see what's going on. So you'll see me draw the rectangles side by side, even though technically they should be one on top of the other. So again, you'll probably see me drawing my pictures something like this, even though technically it should really be the inner rectangle should be right here. And one more time when we set this up, we want to be thinking when we know we have to use washer method, so we're rotating here around the x-axis. And I know I have to use washer method, not disk method, because I've got this empty space here between the solid or the region and the axis of rotation. Whenever you have empty space in between your region and your axis of rotation, you're going to want to use the washer method. Okay, so pi integral, this is a dx problem because we have vertical slices. So I'm going from x equals a, that's where my region starts, all the way over here to x equals b. And then it's this outer radius, big R. So that's vertical distance, top y minus bottom y. And this top y right here is touching y equals f of x. So it's f of x squared, pi r squared, minus, and then we'll do the same thing for finding the volume of that inner disk. So this is my little r here. Vertical distance, it's the top y minus the bottom y. And this top y right here is just the y equals g of x. So minus g of x squared dx. And it's perfectly fine if you'd rather do it as 2 separate integrals and just subtract the answers. We can use that sum difference property for integrals, or you can put them together in a single integral. Now we know the equations for f of x and g of x, so we can actually work this one out. We have to figure out our interval. So this one here starts at the origin and it goes to this point of intersection right here. So now I have to figure out where does f of x intersect g of x. And we know we've got the equations y equals x and y equals x squared. So to see where they intersect, we would set them equal to each other. So where does x equal x squared? And for that, we can subtract x on both sides. So we'd have 0 equals x squared minus x, and then factor out an x, 0 equals x times x minus 1. And we can see that the solutions would be x equals 0 and x equals 1. So we already have the x equals 0, that's the one at the origin. And here x equals 1. When x equals 1, what does y equal? You can look at either one of your equations. When x is 1, y is 1. So my integral is going from 0 to 1. This is a dx problem, so I'm using the x coordinates, but in this case, the x coordinates and the y coordinates are equal. Then I need my function f of x. So that's the linear function, just y equals x. Right here, y equals x. Let me clean up this picture a little bit. We got a lot going on here. Okay, so right here, this is y equals x. And at the bottom, right here, we have y equals 0. So top minus bottom, x minus 0 squared. That's my outer radius. That's my capital R. That's my big R squared. Minus, and then for my inner radius, the empty space, we're going from here, and that's the y equals x squared, to here, which is also y equals 0. So x squared minus 0, that's top minus bottom for the vertical distance there, squared. That's my little r squared dx. And we can simplify that. That's pi integral from 0 to 1, x squared minus x to the 4th dx. And then we find our antiderivatives, so x cubed over 3 minus x to the 5th over 5. Evaluate from 0 to 1. When we sub in 1, we get 1/3 minus 1/5. When we sub in 0, we just get 0. So that is giving us 2 pi over 15 for our volume. Here we have our general formula for the washer method. If we're using a vertical slice, it's a dx problem. And again, we've got pi radius squared times height, and then minus, same thing again with the inner radius, pi radius squared times height. So we're really just doing two disk methods and finding the difference. I think it's easier to just put it all in one single integral. So in that case, we want to do big radius squared or outer radius squared minus little radius squared or inner radius squared. Now in this problem, we have a region defined by y equals x and y equals x squared. So here's our region right in here in between these two curves. We want to rotate that region about the line y equals 2. So we're rotating it about this line right here. And when we do that, if you can just imagine taking that yellow shaded region and rotating it around the line y equals 2, all of this right here is empty space. And then as you rotate it, you also have like all of this empty space over here as well, right? So because we've got that empty space between the axis of rotation and the region, we're going to want to use washer method here. So for washer method, we want to draw the reference rectangles. And they're already drawn in the picture here. Sometimes it is a little confusing how or where exactly to draw your rectangles. But rule of thumb here, one side of your rectangle has to be touching the axis of rotation. Has to be, always. So you're going to draw from the axis of rotation, right here, the y equals 2, and you're going to draw all the way down to the outer function, just until you hit the outer function, and that's where you draw that rectangle. So that's going to represent that big R, that outer radius. And when you go to draw your second rectangle, your inner radius, you go from the axis of rotation just to the inner function. And that's going to be your little radius, little r. Now setting up the problem, our volume is going to equal pi, and then we'll integrate. This is a dx problem because we have a vertical slice. We're going to integrate from x equals something to x equals something. Where does our region start? Where does it stop? What interval are we working on? And we're looking at x coordinates. So we're going from right here, x equals 0, to right here, following that down right there, x equals 1. Now we want big R squared minus little r squared, the outer radius. The outer radius, I'm looking for this vertical distance right here. So to get vertical distance, you always do the top y. So the top of this rectangle is touching y equals 2, minus the bottom y. The bottom of this rectangle is touching y equals x squared. So top y minus bottom y, 2 minus x squared. That's my radius, and I still have to square that. Sometimes what I like to do when I'm setting up the problem, just so I don't forget to square things, because it's easy to forget to square, especially when the radius itself already has a square in it. But you know your setup is going to be big radius squared minus little radius squared. So sometimes I just go ahead and, almost like I'm making a template for myself, I just write that and then I go back and fill in the blanks. So that big radius is 2 minus x squared, right? Top minus bottom. Then the little radius, we want this distance right here. So again, we take the top y value, and the top y here is touching y equals 2. And the bottom y is touching y equals x. Not y equals x squared, but the equation y equals x. So this is 2 minus x for that inner radius. Now we have our problem set up. We're ready to compute the answer. So I'll do a little bit of simplifying. In order to integrate this, we're going to want to FOIL these terms out or expand these terms. So first times first, minus twice the outer product, so minus 4x squared, plus last times last. Now I have to FOIL this and distribute a negative sign. So here first times first is 4, so minus 4. And then minus 4x times minus 1 be plus 4x. And then plus x squared times the minus 1 is minus x squared. I have some like terms that I can combine. So we've got a minus 4x squared, a minus x squared. That's going to be minus 5x squared. I've got this x to the 4th, minus 5x squared. I've got 4 minus 4, so that's 0. And then just plus 4x, it looks like, dx. Okay, now we integrate. So x to the 5th over 5 minus 5x cubed over 3 plus 4x squared over 2 from 0 to 1. When I sub in the 1, get 1/5 minus 5/3 plus 2. When I sub in the 0, I'm just going to get 0. That is pi times 8 over 15, or 8 pi over 15. Okay, our next example, we'll find the volume of the solid obtained by rotating the region bounded by y equals x and y equals x squared. So same region we were looking at before, but this time we're going to rotate around the line x equals -1. So that would be this line right here, x equals -1. We're going to rotate around that line. So I would start by sketching the graph, so we already have a head start here, and then figuring out the interval that we're working on for our region. So here the x is 0, and here if we follow that down, the x value is 1, and I know this because it's the same graph we were working on in the last problem. So these points of intersection were 0, 0, and 1, 1. We're rotating around the line x equals -1. So I want to draw my reference rectangles. And if this is my shaded region right here that I'm rotating, I definitely have empty space all in here. So washer method, we're setting up washer method. Our outer rectangle is going to go from the axis of rotation to the outermost function. Just draw a rectangle there. That represents the outer rectangle. And then the inner rectangle goes again from the axis of rotation to the inside function. So right about there. Because these are horizontal rectangles, this is a dy problem. I'm not able to draw vertical rectangles for this problem because we always have to draw the rectangle perpendicular to the axis of rotation. That's the key to setting up this washer method. So this is going to be a dy problem. My volume will be pi, and then I'll have to integrate. These are going to be y values now, and it's going to be outer radius squared minus inner radius squared dy. That's my setup. Okay, so what's our outer radius? Well, now I have horizontal distance. So the right side of the rectangle is touching x equals what? Well, the equation that I have for that graph is y equals x squared. Y equals x squared. But I need to know what that is if I solve for x in terms of y. So we'll solve this equation for x by taking the square root of both sides. And we get x equals plus or minus square root of y. So we have to think about which one of those we're going to use. Is it x equals positive root y or x equals negative root y? And the x equals positive root y gives us positive x values. X equals negative root y gives us negative x values. So this point, no matter how I draw my rectangle, like how far down I draw it or how high up I draw it, this point is always on the positive side of, or the right side of the parabola, the side that's to the right of the y-axis. So I want the positive root. So x equals square root of y. The equation for the left half of the parabola is y equals negative root y. Okay, then the left side of my rectangle is touching x equals negative 1. So for horizontal distance, we do the right x minus the left x. So root y minus negative 1. And that double negative makes it root y plus 1. Now for the inner radius, we're going to do something similar, right? The right side of here is touching x equals what? Well, we know that graph is y equals x, which means x equals y. So that's pretty easy, x equals y. And the left side of that rectangle is touching x equals negative 1. So for that horizontal distance, we do the right x minus the left x, y minus negative 1. And there's our setup. Oh, I haven't done my lower upper limits of integration. So because it's a dy problem, now I have to use y values, and I only labeled the x values, but this is the point 1 comma 1. So we're going to go up to a y value of 1, and we're going to start, this is 0, 0 down here, so we start at 0, and we're integrating up, 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 until we hit y equals 1. So 0 to 1. Now we worked out the last several examples by hand. This one I'm just going to go ahead and do on the calculator to save us a little bit of time. And this one turns out to be pi times 1/2, or pi over 2. So here's what our washer method formula looks like when we're doing a horizontal slice. Very similar to the dx version of the formula, but we know we're using y values to define our interval. It's a dy problem. And then when we write the r squared, the big R squared and the little r squared, you should be using the variable y. And you get the y by solving your equations for x. When you write your equations in the form of x equals some function of y, you're going to have y's as your variables in these expressions. So I would encourage you to pause the video here and try this problem on your own. Find the volume of the solid formed if we revolve the region bounded by y equals 2x, x equals 3, and y equals 0 about the line y equals negative 2. So I haven't provided the graph for you here, but this is typically what a problem might look like. And you should start by sketching a graph, find those points of intersection, determine what your interval is that you're working on, and then we want to figure out, is this a dx problem or a dy problem? And that's going to be based on your axis of rotation, because you always want to draw those rectangles perpendicular to your axis of rotation. So pause here, see if you can set the problem up, and then you are welcome to actually do the integration on your calculator. And here's what we should be getting. So the volume is 72 pi, or about 226.195. We see on the far left, here's a graph of the region. It's not closed off, but it would be like so. And we're asked here to rotate the figure around the line y equals -2. So here's the axis of rotation. And we do have then empty space in between the region, our solid region, and the axis of rotation. So here's the region that we're rotating around that line. And then the two graphs on the right are trying to show you what that might look like in 3 dimensions when you rotate that figure. Okay, next example again. I would encourage you to pause the video here and try setting this one up on your own. We have the same region bounded by y equals 2x and x equals 3 and y equals 0, but now we're going to rotate around the line y equals 6. So here's our region, and I'm going to shade the region. We're rotating around the line y equals 6, which is this line right here. I'm going to rotate there. And here's our empty space in between our figure and our axis of rotation. When you draw your outer rectangle, it should go from your axis of rotation to the farthest edge of the figure. So right there's your outer radius, and when you draw your inner radius, go from the axis of rotation to that inner function there. And we can see in 3 dimensions, it's kind of like you've got a funnel sitting inside of a can of tuna. And so we've got some empty space in the interior, but then we have a big solid section on the outside. And this one also happens to give us a volume of 72 pi. Okay, try this next one. It's the same region, y equals 2x, x equals 3, y equals 0, but now we're going to rotate this around the y-axis, Now the graph looks a little bit different just because the scale is different, but it is that same region that we were looking at in the last 2 examples. So there's our region, and we want to rotate this around the y-axis right here. So we do have this empty space in between the axis of rotation and our region. When we draw our rectangles for the washer method, we go from the axis of rotation to the outermost function, that's the outer radius, and then the inner radius from the axis of rotation to the inside function, the inner function. So there's our little r. You have to draw your rectangles perpendicular to the axis of rotation, so we don't have a choice in this problem whether it's going to be dx or dy. This one has to be a dy problem because we have horizontal rectangles. And the volume here is 36 pi. Okay, our last example, pause the video here and try this one. Again, it's that same region, but this time we're going to rotate around the line x equals 6, the vertical line x equals 6. So here's our shaded region. We're rotating around x equals 6, which is right here. So we're rotating around that. And we have empty space in between axis of rotation and our solid region. So we're going to use the washer method. Outer rectangle goes from the axis of rotation to the outer function. So that's our big radius. And then the inner rectangle from the axis of rotation to the inside function there. This, again, is a dy problem because we have horizontal rectangles, dy. We have to go perpendicular to the axis of rotation when we're using the washer method. So horizontal distance, remember, just doing the right x minus the left x. So here x equals 6, And here x equals, we might have to solve that equation for x. That came from this equation here, so if y equals 2x, x equals 1/2 y. 1/2 y. So outer radius 6 minus 1/2 y squared. And then similarly for that inner radius, we've got x equals 6 on the right, x equals 3 on the left, so 6 minus 3, right minus left, squared. And this one also has a volume of 72 pi. Once again, I can't emphasize this enough. You always need to draw that reference rectangle perpendicular to your axis of rotation. And it may seem like just extra work to sketch the graph and draw the rectangle, but it really does help to avoid making a mistake in your setup. If you feel like you need some more practice, here are some more good practice problems where you're defining a region, rotating it around. We've got some vertical line problems, some horizontal line problems for your axes of rotation. So if you want to pause the video here and try a few more, you can. These are calculator questions, so you can use Math 9 to actually do the integration. The most important thing right now is to practice getting the setup correctly. The most important thing for right now is to get the setup correct. And here are the solutions for those examples. Critical thinking question for this lesson. How are the disk method and washer method related? There are definite similarities, but there's also some differences there. How are they related? And under what circumstances would you use the disk method versus the washer method? Thank you guys for tuning in. In the next lesson, we're going to see how to find the volume of a solid of revolution using an entirely different method called the shell method, or the method of cylindrical shells. We'll see you guys next time.